Let's take another look at the indefinite integral. Our process is, start with a function little f. We're going to assume it's a derivative. I want to find the function that it came from. So we're trying to undo the derivative process. Now, if we can find a function capital F that does that, so that just means capital F prime is equal to little f. We'll call capital F an antiderivative. Then, the language that we use to state that, we're going to say the indefinite integral of f of x with respect to x is equal to capital F of x plus a constant. So, what this says over here is, we have f of x. Find me the function that has derivative f of x. Then, we're going to get our capital F of x, and then we add a constant because once I found one antiderivative, capital F of x, we get all others by adding numbers. Now, once we found our capital F of x, we can go ahead and put capital F prime into the equation over here because that's just equal to f. So it's going to give us a useful identity. That's going to be indefinite integral of capital F prime dx equals capital F plus a constant. So the idea here is if we take the derivative of capital F, take the indefinite integral, they cancel each other out. Okay? And then we just fix that by adding a constant. So that's the way you should think of the processes here. Take the derivative, take the antiderivative, they should cancel. Now, this is going to give us a recipe for getting new formulas. So for instance, let's put in sine of x for capital F. Then we have this equation here. Then you'll note if I take the derivative of sine of x, we're just going to get cosine of x. So that gives us the equation for the indefinite integral of cosine. Of course, we check our work. So we're going to take the derivative of the right-hand side. Okay, if I take derivative of sine of x, that's going to give me cosine of x. And that should match what we have in our integrand. If we put in cosine of x, okay, so we get our equation. Then I'm going to take the derivative of cosine of x. That gives me minus sine of x. So if I push the minus sign to the other side, get the equation indefinite integral of sine of x. It's going to be equal to minus cosine of x plus a constant. Okay, one thing you'll note when I push the minus sign over, okay, I don't push it into the constant. The constant is an undetermined number, so if I hit it with minus sign or multiply by 2 or whatever you want, it's just going to stay constant. Okay, again, check your work. Take the derivative of minus cosine. That's going to give us, okay, so we have a minus sign out in front. Derivative of cosine is minus sine. So we're going to wind up getting sine of x, and that matches my integrand. Let's apply our formula to the other basic trig functions. So to get our table, what do? Down the right-hand side, we put our basic trig functions. To get to the left-hand side, I just take the derivative, put it in as the integrand. So since the derivative of tangent of x is secant squared of x, we have the indefinite integral of secant squared of x dx equals tan x plus a constant. Okay, note here, this is just our usual rewriting one function as a derivative of the other. So it's just a language trick. Now, for the lower three, okay, so take, for instance, cotangent of x. Its derivative is going to be minus cosecant squared x. So when we put that in over here, we can take the minus sign and move it to this side. Now, you might be wondering, what about the indefinite integral of, say, secant of x or tangent of x? We'll get those later on, but we're going to need a lot more technique. Now, if you note, in our table, it's going to break into two groups of three, just like for the derivative. Okay, for the derivative, you focus on the inputs. Here we're going to focus on the outputs. So note, for the top three, okay, the outputs don't have the co-prefix, so they get the plus sign. For the lower three, okay, each has a co-prefix, so they pick up the minus sign. Then note, for cosine and sine, the way you remember whether you get a plus or minus sign, take the derivative, do the opposite. So for instance, for cosine, if I take the derivative, I get minus sine. If I take the indefinite integral, I get a sine. So these are always going to be one or the other. Let's take a look at some examples. First, we'll have indefinite integral cosine of a half x minus sine of a half x, quantity squared, with respect to x. Now, this is in our list, and it doesn't look like anything we immediately recognize. So the idea is going to be, okay, whenever you have trig functions showing up, trig identities aren't far behind. So let's see what happens. Now we're going to expand this. So I'll have a cosine squared plus a sine squared. The angles match up, so that's going to give me a 1. Then for the middle term, we'll have minus 2, okay, cosine times sine. So we can pull out the double angle identity for sine. So sine of twice an angle equals 2 times cosine angle, sine of your angle. So this is going to be equal to sine of 2 times a half x. Now, when we simplify, we're going to have indefinite integral of 1 minus sine of x with respect to x. Each of these we can do, so we can do them one at a time. So first, if I do the indefinite integral of the 1, that's a constant, so I just attach an x. So it gives me x. Then for the sine of x, okay, if I take the derivative, I get cosine. So the indefinite integral is going to be minus cosine. So we're going to wind up with x plus cosine of x plus a constant. Of course, you check your work. So we're going to take the derivative. When we do that, we get 1 minus sine of x. And that's just going to match up with our reduced expression here. Now, if we want to check against, okay, the original integrand, so the idea might be, maybe we made some mistakes going from here to here. We could check at a few points, and then, okay, that might be enough to make us believe it. So let's try the points, x equals 0, x equal to pi over 2. So we're trying to see if at these points, 1 minus sine of x equals cosine of a half x minus sine of a half x, quantity squared. So if we put 0 in each of these, okay, sine of 0 is 0, so this will give me a 1. Then up here, if we put in 0, we'll have cosine of 0, which is 1, minus sine of 0, which is 0. So we get a 1 squared, which is 1. So if we put 0 in, it checks out. If I try pi over 2, okay, here, pi over 2, put that in the sign, you get a 1. So we get a 0 coming out. Then here, if we put in pi over 2, we have cosine of pi fourths minus sine of pi fourths. They're both square root of 2 over 2. So we have a 0 squared, which is equal to 0. So we at least agree on these 2 points. For our next example, we have indefinite integral cosine of x over 1 minus cosine squared of x with respect to x. Now, this doesn't appear in our list, so we're going to need to manipulate until we get something that does appear. If we take the 1 minus cosine squared, we can write that as sine squared. And then we can split what's left over into 2 functions. So if cosine over sine, 1 over sine. By definition, cosine over sine is cotangent, 1 over sine is cosecant. Then this appears in the list. So that's going to give me minus cosecant of x plus a constant. Now note, since we have the co-prefix, we're going to pick up the minus sign. So that's a small check. Now, of course, we check our work. So derivative of cosecant, it's going to be minus cotangent cosecant. The minus signs go away. And then we get from here to here. Now, if we're worried about matching up to the original integrand, we can check as many points as we need to until we're convinced. So for here, we're just going to check x equal to pi over 4. Now, we're going to put pi over 4 into our check here, the derivative. And then we're also going to put it into the integrand. So that's right here. So for our check, if I put pi over 4 into cotangent, it's cosine over sine. For pi over 4, they're equal, so we get a 1. And then for cosecant, that's 1 over sine. So we 1 over square root of 2 over 2. Flip it up. We have 2 over square root of 2. The 2 can be written as square root of 2 times square root of 2. Cancel, and we're left with 1 square root of 2. Now, for the integrand, so we're going to have cosine over 1 minus cosine squared. So we'll have square root of 2 over 2 over 1 minus square root of 2 over 2 squared. Square root of 2 over 2 squared is going to be 1/2. So I'll have a half in my denominator. Then I'll multiply top and bottom by 2. So that's going to leave me with a square root of 2 and our work checks for that 1 point.